Hi everyone, Ryan here. Haven't put out too much content the last few weeks. I've been in the process of buying a house, and it turns out that's a little bit on the time-consuming side. But I have been researching a few things, and one thing that kept coming up in the things I was researching was the sun and our understanding of it. And when it comes to the sun, I feel like most people don't have a really deep understanding of it. I mean, I didn't. So I wanted to just make this a video just about the sun and why it's so important. That's why I titled this that the sun is the most important thing for anyone to understand. Um, First off, the sun makes all the food that we eat. I don't know about you, but I love food quite a bit. It's also the main driver of energy, whether it's direct through solar or indirectly through fossil fuels or hydro. And the sun controls the climate to some degree. It's one of the variables that factors in both historically and presently. Obviously, there's other variables as well, but the sun drives some of those variables directly and others indirectly. There's also, in the current era where we're very focused on technology and satellites, smartphones, all this stuff, the sun drives solar storms, which can interfere with this technology. And if you want to understand the global electric circuit, the sun is an integral part of that. Another very unique thing about the sun is that it's so close to us. It's this big, giant, galactic ball of energy right on our doorstep that we can send satellites out. And we can study even from near-Earth orbit. The SDO, Solar Dynamic Observatory, is just there in near-Earth orbit, and it's given us some of the best data that we've ever gotten on the sun. It's right there. It's like a little laboratory right in our solar system that we can use to learn more about the universe and the Milky Way and just the nature of energy and physics itself. And then of course, something I kept running into is that we think of the sun as being settled science, but it's really unsettled science. There's a few different conflicting models for the sun, and there's new data that's constantly coming out. So it's an ever-changing target. It's not the same sun that we all learned about back in high school. The most important thing to understand when it comes to the sun, I would say, would be the 11-year solar cycle. This 11-year solar cycle, well, it's not exactly 11 years, it's plus or minus a couple of years, but it averages out to about 11. This measures the time it takes for the magnetic fields of the sun to flip. So the north becomes south and the south becomes north. And it's very rhythmic. I think of it like the heartbeat of the sun. It's just every 11 years, pulse, 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 This was historically tracked by sunspot counts, going all the way back to the 1600s. And they were measuring the amount of sunspots on the sun using some clever telescope imaging to a wall in the back of their observatory there. And they were able to track the number of sunspots on the sun. Sunspots are magnetic loops on the surface of the sun. Typically, a little sunspot area can be up to 1,000 times more magnetic than the area around it. And they almost always appear in pairs. So there will be one sunspot that's like a north magnetic field and another sunspot that's a south magnetic field. And you'll have these magnetic loops arcing in between them. Sometimes you'll have a big sunspot that's like a north node, and then you'll have a whole bunch of little small sunspots around it that'll be like south magnetic fields, and you'll have little distributed magnetic arcs between them all. But the charges even out. Over the course of this solar cycle, you'll see that there's lots of sunspots during solar maxima when the fields are in the process of flipping and all these magnetic lines are all interwoven. And then there's hardly any sunspots at solar minima when you have that nice, neat dipole and everything is nicely ordered. So these sunspots are kind of like a function of the chaos in the magnetic field there. During the course of this cycle, you start off, during the course of this cycle, you start off at minima, and as it's shifting to maxima, as the fields are shifting, the sunspots start appearing at about 30 degrees north and south latitude. And then over the course of the solar cycle, they drift towards the equator over those 11 years before resetting back at that 30 degrees latitude in the next cycle. And this is known as a butterfly diagram. They're able to actually track this over the cycles. And you can see a clear pattern here in the way that these sunspots move. A couple notable details here. The sun spins faster at the equator. It spins about every 27 days at the equator, and it spins slower at the poles, so it spins about once every 35 days at the poles. And the axis of rotation for the sun is shifted slightly. So the axis of rotation is 7 degrees off from the ecliptic plane where all the planets and Earth and everything reside on. And the axis of the magnetic field changes a bit, but it's offset from that a little bit. So you don't have like a perfect up and down system. There's some variability in there. Sunspots historically have been a very ingenious way of measuring the magnetic field, but now in the era of satellites, it seems like a crude way to measure this in hindsight. You're basically just measuring magnetic abnormalities that happen to pop up on the surface of the sun, when now we have the technology, we can just measure the magnetic field. So hopefully we'll get better data sets as we progress moving forward. All right, so let's dive into how the magnetic pole flip actually happens for a minute. You start off at solar minima, and you have this nice, neatly ordered dipole where you have a north pole up here, a south pole down here, and then a neutral current sheet, a heliospheric current sheet they call it, in the middle, which is at the equator and even at the equator. So throughout the solar system, you have north magnetic charges moving along one side of the ecliptic, south magnetic pole charges moving underneath it, and then on the ecliptic, you have this neutral charge that the solar wind is driven on, causing an electric current. As these poles start to flip, they lose their dipole tendencies and they become more of like a quadrupole or octapole, where they just have all these different active regions, and each of these active regions has different magnetic lines coming off of it, and they all twist into each other and make a big old mess. This causes more sunspots and space weather too, because as you have these magnetic loops coming off of these sunspots, when those cross into each other, when they short circuit, that's when you get solar flares. That's when you get, coronal mass ejections and stuff. So that's the stuff that's headed towards Earth that causes, satellites to go down and radio blackouts and stuff. I got a great video on that. You can check out my channel about how the sun affects comms. So eventually it goes through this big period of chaos, and then it settles back into a solar minima where you have this nice, neat dipole, except the poles are reversed now. And that happens every 11 years. That's the solar cycle, the heartbeat, I call it. There's larger cycles too. We have what's known as grand solar minimums and grand solar maximums as well. There's a few different ways they measure this. Over the last 400 years, we have direct sunspot readings along with historical records into, crop growing and temperature and everything. So we have direct measurements going back to the Maunder minimum in the 1600s and the Dalton minimum in the 1800s. And then they were able to use tree ring and ice core data to extrapolate beyond that and find evidence of previous minimas that also tie into, historical events. We have like the Oort minima, the Wolf minima, Sporer minima, the medieval warm period. And these all, tie into food growing, volcanism, climate, things that affect the human species here on Earth. My buddy David over at the Adapt 2030 channel is an expert on this subject. Check him out. He's got a bunch of great videos on it. So what I want to know is, what exactly is the sun? We learned one thing growing up, but we have this whole host of satellites now. We got the SDO, the Parker Solar Probe, Wind Satellite, Ulysses, Helios A and B, etc. Lots of satellites up there. What can we learn from all those to improve our understanding on solar physics? The conventional understanding, and what I was taught in college, I took astronomy and astrophysics in college, and what I was taught is that the sun is a big nuclear ball floating around in space that has us trapped in its orbit. That's really all there is to it. It's a bunch of nuclear reactions in the core there, and then there's a convection zone around it, and these fluids, these magnetic fluids, will travel around in various loops in there, and that loop creates an electric current, which then creates a magnetic field via induction. And that's pretty much as we were taught. I remember we kind of just brushed through that topic over the course of like a week or so, and then moved on to more exciting topics after that. I don't even know if it was a week. It might have just been a couple days. I think there's room for us to improve our understanding on the sun for sure. So the conventional explanation for why we have this 11-year pole flip, this solar cycle, this heartbeat of the sun, is the differential rotation around the sun. So remember when I said the equator rotates once every 27 days, but the poles rotate once every 35 days. So the equator is rotating a lot faster. So since the explanation for what creates the pole shift is based on the convection loops in the convection zone there, the argument is that as the equator rotates faster, it twists those convection loops out of place, and then you end up with the big mess that we see during solar maxima, where the magnetic fields are all over the place. And then they spin a bunch and then settle back down into a new minima. So that's the conventional knowledge behind this. It looks good. It looks good, at face value. There are some issues. For one, it has trouble predicting solar cycles. We don't have the ability to accurately predict solar cycles at the current time. And so in my head, I'm thinking, well, if we can't predict it, then we don't know every single variable, so there's more to learn. That's the way I view these things. Until we can accurately predict it all the time, I think that there's still, room to expand there. It's also, we're limited very significantly by the electromagnetic activity around the corona of the sun, the very outside of the sun, the photosphere they call it. It's very electromagnetically unstable, and if we try to bounce any EM radiation off of it or shoot anything into the sun to get measurements back, that outer sphere around the sun is basically just going to wipe out all that radio waves, and it's going to just be a radio blackout. We're not going to see anything beyond that exterior of the sun, with the one exception being helioseismicity, which I'll touch on in a minute. But even on NASA's own website, they still say that the formation of the magnetic field of the sun is still mysterious. So even the experts are admitting that there's more to learn, which I think is healthy. So now that we've covered the conventional theory behind the sun, I want to touch on the double dynamo theory, which is I think is very cool. This was presented by Professor Valentina Zarkova, a very gifted Ukrainian astrophysicist, particle physicist, currently working out of the United Kingdom. She did a bunch of calculations based on solar cycles 21, 22, and 23, and in her calculations, using this mathematical model involving eigenvectors, she determined that there was a second magnetic field interfering with the surface magnetic field. And the two of them were combining to create what we know of as the solar magnetic field. And so this is known as the double dynamo, because there's not one dynamo creating the field, but there's two, and they construct and interfere with each other. So sometimes they make the waves, sometimes they line up and make their wave extra strong, and sometimes they detract from each other and make the wave weak. She predicted that this would be due to two layers of circulation in the convection zone. One would be going one direction at one speed, and another would be going another direction at another speed, and they would be creating two separate magnetic fields that could then basically be combined to form one magnetic field. Using this model, she was able to accurately predict previous solar cycles beyond her data set, and she was also able to predict some of these grand solar maximas and grand solar minimas. So she's been the first that I know of that was able to put forward a working model for what causes these larger 200-year, 400-year cycles. Cool thing here is right after she presented her theory, another team out of Stanford University, Zhao et al. In 2013, basically confirmed her theory using the HMI on the SDO, the Solar Dynamic Observatory, has a helioseismic scanner on it that can measure the speed of acoustic waves that they shoot at the sun at different angles, and it can measure how fast these acoustic waves move through different sections of the convection zone there. And so using their data, and they had some pretty good data, they were able to basically figure out that there was two separate counter-rotating layers in there moving at different speeds. And they were even able to put forward what speed these layers were moving at to create which magnetic fields. So they basically confirmed Valentina Zharkova's theory then in 2013 that that's what was creating the model. That's what was creating the field. This is significant because, as you can see here from this graph, this is the extrapolated mathematic model from Valentina Zharkova's work. She's able to predict these grand solar minimas and grand solar maxima based off the destructive or constructive magnetic wave interference there. And she predicted that we are going to be entering a grand solar minima over the next couple decades. So we'll just have to wait and see how that plays out and keep an eye on it. And we're towards the end of the video now, so we can go a bit off the reservation. When I see those counter-rotating, those counter-rotating fluids inside the sun creating these magnetic fields, the first thing that comes to my mind, because I have a pretty good interest in plasma physics, is a Birkeland current. And so a Birkeland current, as you can see here, these are the currents that, create the auroras that we know and love from their beautiful northern lights photos up in Finland or northern Canada. And these currents are basically just big electric currents that travel around, and they're composed of counter-rotating shells of different polarities. There's a group of physicists that think of themselves as the electric universe branch of physics. This would be like your Hans Alvin, Jurgens, Wal Thornhill, Donald Scott, a few others, many others. And these guys are putting together working models for how the universe, how different galaxies could all be connected through these huge electric currents that travel through the universe. And in their model, and they're kind of viewed as, like fringe scientists, but they raise a lot of good points and they're able to answer some questions that conventional physics cannot answer. Their model for the sun is that it's a plasma sphere, more or less, and it's formed during what they call a Z-pinch between a couple Birkeland currents. When they twist together, this creates a concentration and energization of the plasma, and that can create what we know of as the sun. And so they have a model for, how like the magnetic field works with the in the electric universe, along with the current sheet and everything. They have a model for that. They are able to answer some questions, some discrepancies about the sun that conventional physics has issues with. For example, the neutrinos being much lower in observation from our satellites than was, initially calculated. If we have all this nuclear fusion going on in there, we should have a lot more neutrinos than are actually detected. Also, differences in the convection liquid speed, the amount of convection going on in the mantle there. And I really just think it's a very, very cool theory. I don't know if it is correct, but I want it to be correct because I think it would make things a lot more interesting. And if it is correct, then solar observations can be scaled easily to, galaxy-wide phenomena, universe-wide phenomena, because, a Birkeland current in one area is going to act the same as a Birkeland current in another area. And it would lead to a massive leap forward in physics and technology overall. We'll see if that's the case, and if that is, the way they want physics to progress. That might get a little woo-woo there. We'll cut that out. So in conclusion, I bet the sun is more interesting than you thought it would be. There's a lot of crazy theories bouncing around. There's new information coming out. The sun controls pretty much every aspect of our existence. And so I think it is singularly the most important thing everyone should know about, but most people just think of it as a fireball off in the sky, or it controls their zodiac sign or whatever. There's some real interesting science behind it as well. Hopefully some of this information can help you impress some friends at fancy dinner parties, and I'll see you next time. I got some other cool stuff that I've been researching, and I can't wait to share it with you. All right, bye-bye for now.